Okay, so thank you for coming. My name is Masato. I'm a researcher of NEC, and he is a co-speaker, Yohei. He's a research fellow of NEC. So today, we'd like to talk about distributed heterogeneous mixture learning on Spark. So first, Yohei starts this talk.
Okay, thank you for coming. So today, we're going to talk about predictive analytics. And NEC is one of the top global IT vendor. And we are providing a lot of predictive analytics services in the market using our own machine learning algorithm, which we call heterogeneous mixture learning. And recently, we are receiving quite big needs from customers for analyzing big data using HML. So today, we are going to explain how we developed a distributed version of HML using Spark. And particularly, to fully utilize the capability of Spark, we solve some of the problems like data shuffling, MapReduce synchronization, and matrix computation. So at the end of this talk, I want you to understand what is HML, how it's useful in the predictive analytics, and taking away some of the technological tips we have addressed. And later part of this talk, we will share a kind of interesting use case of distributed HML that is the cache balance forecasting for massive amount of ATMs. So let me start from what is HML. So these are predictive analytics services, a part of predictive analytics services that NEC is providing in the market. For example, energy, water, operation management, that is, we are predicting the demand of water or energy, and then optimize its production on distribution plan. Or like how many sandwiches will be sold in a retail store, and then optimize the number of order counts. And smart transportation is a very hot topic in the market. And a very interesting use case we have developed very recently is driver risk management. Basically using sensor information, driver information, human resource information, by combining all together, we produce a prediction of the risk of accident per driver, and then assess the appropriate training. Preventive maintenance, churn retention are very common use cases and very important for NEC. So we are providing this kind of predictive analytics services based on single algorithm that we call HML. So HML basically analyze different type of data sources and explore the multiple formulas, not a single formula, but it discovers multiple formulas. And at the same time, which formula holds in what kind of situation. So based on the transparent data segmentation and accurate prediction of the formula, it produces prediction. Well, let me give you a very simple, naive example of how HML performs. Like this is a model for health risk prediction. So like a gender and the height, so that kind of segmentation is derived by HML first. And then for individual segment, it uses like a different risk factors, like for female, weight, sports T, or tall man, age, beer, wine, smoke. So by changing a different formula in a different situation or different condition, HML can produce very good accurate prediction. So let me explain two kind of advantages of HML. So we know that deep learning is now a very hot topic in this Spark Summit. And NEC is, of course, developing a deep learning-based solution. But in our enterprise customers, like enterprise business application, healthcare, social infrastructure, those customers basically don't like the black box predictor. So they have to understand why predictor predict in this way, or what's the reason of this prediction. So in that case, predictor need to be not just accurate, but to be transparent. It must produce a reason of the prediction. So this is one of the key features of HML. And If you are a data scientist, you might think that this is nothing but the, traditionally data scientist is doing in manual, like detailed case, partitioning the data by day of the weekend, or night and daytime, or sunny day, rainy day. They partition the data and fit the model for the individual segment and find a good, looking at the fitting score, it's not good, then they change the segment and repeat that kind of procedure until they find a, accurate prediction model. And the beauty of HML is to automate that process, or, fully automate that process. So the number of segment, the number of features for each segment, and what kind of predictive formula, that is automatically determined purely by machine learning algorithm from data. So let me see how HML works. So there are two key procedures in HML. One is data segmentation, and one is feature selection. So data segmentation process find, of course, data segment. In this case, so this segment is based on the locational feature, and this segment is based on the weather feature, and the number of segment is 3. This is also automatically determined by HML. And once it finds a good segmentation, it now finds a good feature for individual segment, and also its coefficient. So the number of, as you can see, the number of features, type of features are automatically discovered by HML, and so this just data segmentation feature selection is not optimal, so it repeats this procedure until it finds the best model. So as I have explained, we have already delivered a lot of HML-based predictive analytics services in the market, and recently we are receiving quite big needs from market on big data analytics using HML. For example, in detail segment, 24 hours, 365 days, 3 years historical data, and 1,000 stores. It becomes a 26 million training samples, or if our customer has a service with 5 million subscribers and 12 months historical data, is 60 million training sample. 26 million, 60 million, it may not be that big for Spark usage, but as you can imagine, it can be easily growth, like 100 million samples. So we develop HML on Spark. That part Masa is going to explain.
Yeah. Okay, so I'll explain the distributed HML on Spark. So first, the reason why we choose the Spark is the Spark's in-memory architecture is very suitable for running machine learning algorithm first. So on Spark, with once data loading from disk, all execution is done in memory first. One of similar distributed computing system to Spark is Hadoop. But unfortunately, Hadoop is not suitable for running machine learning algorithms because Hadoop requires multiple slow disk accesses in its execution. And powered by Spark, we can treat unlimited scale of training data. Spark is a scale-out MapReduce architecture, so Spark can increase the memory and CPU power by just adding executor servers. Okay, so here, this figure illustrates the architecture of distributed HML engine. So data scientists can use the Python interface of distributed HML through the Jupyter Notebook. And the interface invokes the core engine of distributed HML implemented by Scala, and it runs on the Spark. And during the optimization process of prediction models, it calls its matrix computation libraries like Breeze and Blast. Okay, so now let me ask one question. Can any implementation of machine learning algorithm run fast on Spark? This is not true. To run the machine learning algorithm fast on Spark, we must address these 3 technical key points. The first one is data shuffling, and the second one is map-reduce synchronization, and the third one is matrix computation. So I'll explain how distributed HML address them one by one. So the first one is data shuffling. Avoiding data shuffling is very important to run the machine learning algorithm fast on Spark. So even if Spark reduces disk accesses, so huge network accesses delays the execution because the network access is very slower than the CPU computation and the memory accesses. So the important point on this discussion is the size of training data. So it's over 10 terabytes. So if we design the algorithm so that it requires to refer all training data, so the executor must shuffle the training data between them. Then so that there are huge data accesses happened. On the other hand, the size of model information of HML is very smaller than the training data. It usually 10 kilobytes to 10 megabytes. So from this observation, we designed the distributed HML so that it merges locally run HML models on executors into one consistent model on the driver. With this design, so there are no data shuffling of training data happened. So let's see the execution flow of distributed HML. So at the first step, data segmentation, so executors build a rule-based tree from their local training data in parallel. So because of the difference of the local training data, the trees might be different from each other. So then the driver merges the trees, and it fixes one consistent tree. And the driver broadcasts the merged tree to executors. Then so move on to the next step, feature selection. So executors perform the feature selection with their local training data in parallel. So in common with the data segmentation phase, so the selected features might be different from each other because of the difference of the training data. So then the driver merges the results of feature selection, and it fixes one set of selected features. Then so the driver broadcasts the merged results of feature selection to executors. And then it continues the cycle of HML algorithm. Okay, so let me explain the first key point again. So the first one is data shuffling. And to address the key point, so we designed the distributed HML so that it merges locally run training data, HML models on executors into one fixed model. So with this design, there are no data shuffling of training data happen. Okay, so let's move on to the second point, the map-reduce synchronization. So as you may know, so Spark is a synchronized-based map-reduce architecture. So on this architecture, waiting for slow executors is seriously degrades the CPU utilization of the system, and it makes the execution time longer. Particularly, machine learning algorithms likely to cause a big gap of execution time on executors because it's a very CPU heavy workload. So let me share one case. So suppose that we designed the distributed HML so that each executor optimizes one predictive formula in parallel. Then, so with this design, there is a big gap of execution time between executors. This is because optimization load, calculation load is varies depending on the prediction formulas. So then, to address this issue, we designed the distributed HML so that each executor optimizes all predictive formulas with equally divided training data. Then, so the execution time is balanced and the waiting for time for slow executors is quite reduced. And finally, the completion time is reduced. Okay, so let me explain the second point again. So the second one is map-reduced synchronization. And to address the key point, so we designed the distributed HML so that each executor optimizes all predictive formulas of HML model with equally divided training data. So then the computational effort is balanced and the waiting time is significantly reduced. Okay, so let's move on to the third one, matrix computation. So machine learning algorithm consists of many matrix computations. So distributed HML also performs many matrix computations like basic matrix computation, matrix inversion, and the combinatorial optimization. And this matrix computations is a major part of computation time of distributed HML. So to accelerate the bottleneck point, so it's a good way to use high-speed matrix computation libraries like Breeze and BLAS. However, if we design the RDD straightforwardly, then so there are many overheads happened to call the matrix computation libraries. So suppose that we design the RDD so that each element contains one training samples. Then, so to call the matrix computation libraries, there are many iterator accesses and wasteful matrix object creation happened in the map partition operation. So these are very huge overhead. So to avoid such a big overhead, we designed the RDD so that each element contains one matrix object with several training samples. Then, so we can distributed HML can call the matrix computation libraries with low overhead. So maybe so this is you might think this is a trivial point, but it has a very big impact for the execution of machine learning algorithms. So yeah, we reserve this one key point. Okay, so by the way, so let me share one more issue of performance degradation of distributed HML. So through the development of distributed HML on Spark, we noticed that the performance is seriously degraded by the long-chain RDD operations. So HML is, because HML is a cycle-based algorithm, so there are many RDD operations happened and they are in a long chain. So if unfortunately the necessary intermediate results of the RDD operations are flushed by the garbage collection, then so the next computation requires the recalculation of the flushed data back to the one available on memory. So this is a very wasteful recalculation, the computation cost. So to avoid such a wasteful computation, we improved the distributed HML so that it cuts the long chain operations periodically by the checkpoint API call. Then, so this implementation can continue the execution without the recalculation of the flushed intermediate data, because the checkpoint API cuts the chain. So, but however, it's not best method to solve this problem, because the checkpoint API issues many issues disk accesses. So we are still exploring the more better method to solve this problem. So if you have any good ideas, please share them with us. We're welcome. Okay, so let's move on to the benchmark performance evaluation. So our evaluation consists of two parts. The first evaluation compares the prediction error of, with algorithms of Spark MLlib. So for this comparison, we choose 3 algorithms from Spark MLlib. So the one is logistic regression, and decision tree, and random forests. And for this comparison, we prepared 4 open data sets from UCI machine learning repository. Then, so this experimental result demonstrates that distributed HML achieves low error compared to the 3 algorithms, especially one complex model like random forests. Then, so the second evaluation compares the performance scalability with Spark MLlib. So this figure compares the normalized processing time between the algorithms and the number of CPU cores. So this experimental result demonstrated that performance scalability of distributed HML is competitive with that of Spark MLlib implementations. Okay, so finally, so let's move on to the evaluation in real use case. So to evaluate the value of distributed HML in real use case, we performed an ATM cache balance prediction with real data. So suppose that the average stock of ATM is $50,000 US. So if we have 20,000 ATMs, the stock size is 1 billion US. So it's a very much cash inventory. So even if we reduce the stock by only 10%, we can invest 100 million US for other purposes. So it's very valuable for economical perspective. But however, if we reduce the stock too much, the risk of out of stock of ATMs increases, and the customer satisfaction is degraded. So for this use case, the high accurate prediction model is very important and valuable. So in this evaluation, we compare the distributed HML and the original or serial HML from the 2 points. The first one is training speed, and the second one is prediction error. So for training speed, so serial HML took 9 days to complete its execution with around 10 million training samples. On the other hand, distributed HML completed it in only 2 hours with 128 times CPU cores. So this means distributed HML achieved 110 times speed up compared to the serial HML. So actually, for this use case, we can speed up the serial HML by running the serial HML on each ATM's training data. But however, this degrades increases the prediction error because the size of training data for each serial HML reduced. On the other hand, distributed HML can use the whole training data, in this case, so around 23 million samples. So distributed HML can achieve the higher prediction accuracy. So finally, so the distributed HML achieved 17% lower average prediction error compared to the serial HML. Okay, so finally, let me summarize our talk. So in this talk, we introduced the distributed HML on Spark. And the HML is a core technology of NAC's advanced analytics. To run the distributed HML first on Spark, we must address the three technical key points. So the first one is data shuffling, and the second one is map-reduced synchronization, and the third one is matrix computation. Okay, so distributed HML is now ready to use, and we are exploring the enterprise use cases with big data for the advanced analytics with HML technology. So if you are interested in HML data predictive analytics and you have a big data, so please feel free to call us. Thank you.
Outstanding. Any questions?
Just curious, any of this stuff is open source?
No, it's proprietary software, so it's not open now. Okay.
Hi, very impressive work. So I have three questions. The first one is, do you find it important to randomly reshuffle your data before you distribute the data to the executors?
First, so distributed HML assumes the training data is already shuffled on before its execution. So the distributed HML algorithm is does not do any shuffling of training data, but we think the Spark architecture can support the shuffling of the
let's say, but
the algorithm perspective we need basically that the merging algorithm. So model merging algorithm need some theoretical condition, and one of it is data is randomly shuffled in advance. So if data is ordered in some way, we have to first randomly shuffle the data.
Okay.
But that he said that Spark can support that part.
I see. So the second one is when you merge the partial trace, and do you do partial aggregation before they reach the driver?
No.
No. Basically, just do the aggregation.
No, but it's kind of easy to make the hierarchical architecture, like a hierarchical merging structure. At the current data size, it's okay. But
I see.
One of the interesting discussion we had is if there's some reason, like data cannot be loaded geometrically, cannot be moved for security reason or something, then we need some kind of driver in each region. Then each driver merges the HML model. Then it upload the model to the global driver, something like that.
I see. The third one is basically there could be some trade-off between the number of workers you have, because it means each worker only get a small portion of your data, and between this number of workers and then the accuracy of your model. And did you do some evaluation of that?
So yeah, we are still evaluating, but so the current setup is the number of partitions is the same of number of CPU cores, and we we confirmed that the performance accuracy degradation is negligible from the other setting.
And one very important phenomenon we observed is that actually, he in his part 110 times acceleration rate. But in this case, even in terms of accuracy, distributed HML performed better. And this is related to some kind of overfitting issue, like a serial HML looking at the overall data. But the distributed HML, local aggregation happens, so that has some regularization effect in the model. And even that kind of even prediction accuracy point of view, distributed version have some advantage over the serial algorithm.
Yeah.
Great, let's give him a big hand.